You think the solar system ends at Neptune. Almost everyone does. When you picture the solar system, when you call up the image that formed in your mind from school textbooks and science documentaries, and those familiar diagrams with the sun at the center and the planets arranged in concentric rings, the picture ends somewhere around Neptune. 8 planets, a few dwarf planets beyond the last one, and then space, the void, the distance between us and the nearest star. That picture is wrong. Not slightly wrong, not missing a few details, wrong in a way that understates the true size of the solar system by a factor of approximately 1,000. Wrong in a way that places the actual boundary of our star's gravitational domain at a distance so far beyond Neptune that Neptune itself becomes a near neighbour, almost as close to the Sun as Earth is by comparison with what actually defines the solar system's edge. The solar system does not end at Neptune. Neptune is at 20 set astronomical units from the Sun. The solar system extends to approximately 30,000 astronomical units from the Sun. 30,000 versus 20 set. The true edge of the solar system is more than 3,000 times farther from the Sun than Neptune. And between Neptune and that true edge, in the 99.97% of the solar system's radial extent that your mental picture has simply omitted, there is something real, something enormous, something that contains more objects than you have ever imagined, in more extreme conditions than Neptune has ever experienced, in a region that humans have never visited and that no spacecraft has come remotely close to reaching: the Oort Cloud. Tonight we are going to think carefully about what the Oort Cloud actually is. Not the vague gesture toward a fuzzy shell of distant comets that most people carry from a single paragraph in a textbook. The actual structure, the actual numbers, the actual scale, the actual physics of what exists at the edge of our star's gravitational reach. By the end of tonight, your mental picture of the solar system will need to be rebuilt from scratch. Not because any single fact has changed, because the scale of what has always been there, waiting to be understood, is larger than anything the familiar solar system diagram can accommodate. If the night is long, stay. Begin with what you already know, because the contrast will matter. Earth is at 1 astronomical unit from the Sun. 1 AU, millioner kilometrov. Light crosses it in invasive minutes and seconds. This is the fundamental unit of solar system measurement, the Earth-Sun distance, the baseline from which everything else is measured. Mars is at 1.52 astronomical units, Jupiter at 5.2, Saturn at 9.5, Uranus at 19.2, Neptune at 30.1. These are the planets, the things your mental picture includes. Beyond Neptune, the Kuiper Belt, a flattened disk of icy bodies extending from approximately 30 astronomicznych jedinic to approximately 50 astronomicznych jedinic. This is where Pluto lives, at 39 astronomicznych jedinic on average, though its orbit is elliptical enough to sometimes bring it closer to the Sun than Neptune. The Kuiper Belt is where the short-period comets come from, comets with orbital periods of less than 200 years, comets that return to the inner solar system on timescales short enough to be tracked by human astronomers. Beyond the Kuiper Belt, the scattered disk. A sparser population of icy bodies extending from approximately 50 astronomical units out to roughly 1,000 astronomical units, with orbits inclined more steeply to the plane of the solar system than the Kuiper Belt. Sedna, one of the most distant known objects in the solar system, has an orbit that takes it from a perihelion of about 76 astronomicznych jedinic to an aphelion of approximately 937 astronomicznych jedinic, nearly 1000 times the Earth-Sun distance. 937 astronomicznych jedinic, nearly 1000 times farther than Earth from the Sun. This seems like the outer edge of anything. Voyager 8, our farthest spacecraft, is currently at approximately 163 astronomiczne jedinice from the Sun. It crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, at approximately 121 astronomiczna jedynica in 2012. Voyager 8 is in interstellar space, beyond the heliosphere, beyond the region of space directly influenced by the solar wind. And yet, Voyager 8 is not outside the solar system, not by a very long margin. The heliopause, the boundary where the solar wind ends, is not the boundary of the solar system. The solar system's gravitational domain extends far, far beyond the reach of the solar wind. Gravity has a much longer reach than the solar wind, because gravity requires no medium to propagate and weakens only with the inverse square of distance, while the solar wind's influence dissipates much more rapidly against the pressure of the interstellar medium. The true gravitational boundary of the solar system, the distance at which the Sun's gravity is balanced by the gravitational influence of the surrounding galaxy, is approximately 1 to 2 light-years from the Sun. In astronomical units, that is approximately 63,000 to 126 AU. The Oort Cloud fills this entire region. Let that number sit for a moment. 126 astronomicznych jedinic, 100,000 times the Earth-Sun distance. Voyager 1 is at 163 astronomicznych jedinic. Voyager 1 has been travelling since 1977, 47 years, and is at 163 AU. The inner edge of the Oort Cloud begins at approximately 2000 AU. Voyager 1 will take approximately 300 years to reach the inner edge of the Oort Cloud at its current speed. The outer edge of the Oort Cloud is at approximately 110 astronomical units. At Voyager 1's current speed of roughly 17 kilometers per second, approximately 61 kilometers per hour, reaching the outer edge of the Oort Cloud would take approximately 30 years. 30 years. This is a number that places the Oort Cloud's outer boundary in a different category from anything else in the solar system that people typically think about. The agricultural revolution, the invention of farming, the beginning of settled civilization, the precondition for writing and cities and all of recorded history, happened approximately 12,000 years ago. The outer edge of the Oort Cloud is 30,000 years away at our fastest achieved spacecraft velocity. You would need to start the journey before the most recent ice age ended to reach the outer edge of the solar system now. 30,000 years, and this is the solar system. Our solar system, the one we live in, the one we think we know. Now let us think about what actually exists in this enormous volume of space. The Oort Cloud is not a sharp-edged shell. It is a diffuse, roughly spherical distribution of icy bodies, cometary nuclei, chunks of rock and ice, ranging in size from meters to hundreds of kilometers in diameter, spread across the outer reaches of the solar system's gravitational domain. The population of the Oort Cloud is enormous by any measure. Current estimates, derived from the rate at which long-period comets enter the inner solar system and from models of how the cloud formed and evolved, suggest that the Oort Cloud contains approximately 2 trillion objects larger than 1 kilometer in diameter. 2 trillion objects, each one a comet nucleus, a chunk of ice, dust, rock, and organic compounds preserved in near absolute zero conditions since the formation of the solar system. Trillion objects in one star's gravitational domain. In the solar system, you thought you knew. For comparison, the asteroid belt between Mars and Jupiter, the region most people think of as the solar system's reservoir of small bodies, contains approximately 1 to 2 million objects larger than 1 kilometer in diameter. The Oort Cloud contains approximately 1 to 2 million times as many. The asteroid belt, with all its bodies, is not even close to the scale of what exists at the outer edges of our solar system. Now let us think about what these 2 trillion objects are, where they came from, and what conditions they exist in. The Oort Cloud objects are cometary nuclei, the solid cores of what will eventually become comets if they are perturbed into orbits that bring them into the inner solar system. They are made of the same material as the solar system's original building blocks: ice, rock, dust, and complex organic compounds, frozen into solid bodies since before the planets existed. The ice is not the ice of Earth's oceans and polar caps. It is not primarily water ice, though water ice is present. It is a mixture of volatile ices: water, carbon monoxide, carbon dioxide, methane, ammonia, frozen solid at the temperatures of the outer solar system. Mixed with rocky material and complex organic molecules, the building blocks of biochemistry, preserved in conditions so cold that chemical reactions that would decompose them at warmer temperatures proceed essentially not at all. The objects in the Oort Cloud are the most pristine material in the solar system. They formed from the same cloud of gas and dust as the Sun and planets, but instead of being incorporated into planets, they were scattered outward by gravitational interactions with the forming gas giants, primarily Jupiter and Saturn, into the distant, cold, undisturbed reaches of the solar system's outer zone. There they have remained, largely unchanged, for 67 billion years. 67 billion years of preservation at temperatures close to absolute zero, in a region so distant from the Sun that sunlight is a faint glow. The Sun, from the outer Oort Cloud, appears as a bright star, no different in apparent brightness from many other stars visible in the sky. Not the overwhelming presence it is from Earth. A bright star, one of many. The conditions in the Oort Cloud are extreme in their tranquility. Temperature, approximately Cheta to Jesit Kelvin in the inner Oort Cloud, approaching 2,7 Kelvin, the temperature of the cosmic microwave background in the outer reaches. Pressure, effectively zero. Density, extraordinarily sparse, even compared to interplanetary space. Light levels, negligible for any purpose relevant to chemistry or biology. An object in the Oort Cloud receives sunlight millions of times fainter than Earth receives. The Sun's gravitational pull on an Oort Cloud object at 50 astronomical units is approximately 2,5 billion times weaker than its pull on Earth. This extreme weakness of solar gravity in the Oort Cloud has a specific and important consequence. The objects there are vulnerable to perturbation by other gravitational influences that would be completely negligible in the inner solar system. The gravitational tides of the Milky Way, the variation in gravitational force across the extent of the solar system produced by the galaxy's mass distribution, become significant at Oort Cloud distances. Stars passing through the galactic neighborhood of our solar system, which happens on timescales of hundreds of thousands to millions of years, create gravitational perturbations that can alter the orbits of Oort Cloud objects. Giant molecular clouds, the dense nebulae from which new stars form, can disturb the Oort Cloud when the solar system passes through or near them during its orbit around the galaxy. These perturbations are the mechanism by which comets from the Oort Cloud are occasionally sent on their long journeys toward the inner solar system. A gravitational nudge from a passing star, from the galactic tide, from a nearby molecular cloud, changes the orbit of an Oort Cloud object just enough to reduce its perihelion, the closest point of its orbit to the Sun, from something safely beyond the planetary region to something that brings it swinging through the inner solar system. This is how long-period comets originate. The comets with orbital periods of hundreds, thousands, or even millions of years comets so recently arrived from the outer solar system that they still carry the pristine chemical record of the solar system's formation, come from the Oort Cloud. They are our only direct samples of Oort Cloud material. Every long-period comet that has ever been observed from Earth, every comet that appeared in the historical record, that amazed ancient astronomers and terrified medieval populations, that was tracked by modern observatories and found to have orbital periods of thousands or millions of years, was an Oort Cloud object that received a gravitational nudge and began its journey inward. And the rate of these arrivals gives us our estimate of the Oort Cloud's population. If you know how often comets arrive from the Oort Cloud, the flux of new comets entering the inner solar system per year, and you know how efficiently the perturbation mechanisms that send them inward work, you can estimate how many objects must be in the cloud to sustain that flux. The calculation gives approximately 2 trillion objects. 2 trillion frozen time capsules from the solar system's birth, preserved in near absolute zero conditions for 400 billion years, occasionally nudged inward by the gravity of a passing star or the galactic tide. Now let us think about the structure of the Oort Cloud more carefully, because it is not a single uniform sphere, but a more complex structure with distinct regions. The Oort Cloud is typically described as having 2 components: the inner Oort Cloud, also called the Hills Cloud or the Hills-Oort Cloud, and the outer Oort Cloud. The inner Oort Cloud extends from approximately 2,000 astronomical units to approximately 20,000 astronomical units. It is not spherical, but rather has a flattened disc-like structure, a thick disk that is concentrated toward the plane of the solar system. This disk structure reflects the fact that the inner Oort Cloud has not yet been fully randomized by galactic tides. The objects there have been less thoroughly mixed and scrambled by external perturbations than objects in the outer cloud. The inner Oort Cloud contains a larger number of objects than the outer cloud. It is denser in terms of object density per unit volume. It is also less accessible to the perturbation mechanisms that send comets inward, because the galactic tide and stellar passages are less effective at disturbing orbits in this region. Objects in the inner Oort Cloud are more strongly bound to the Sun and require larger perturbations to be sent on inward trajectories. The outer Oort Cloud extends from approximately 20,000 astronomical units to approximately 100,000 astronomical units. It has a more spherical, shell-like structure, the result of billions of years of gravitational scrambling by galactic tides, stellar passages, and other external perturbations. The outer cloud is sparser than the inner cloud, but is the primary source of long-period comets that reach the inner solar system. The outer boundary of the Oort Cloud, approximately 100,000 astronomicznych единиц, or roughly 1,6 light years, is not a sharp edge but a gradual transition. Beyond this distance, the Sun's gravity is so weak relative to the gravitational influences of the galaxy that objects cannot maintain stable orbits around the Sun. They would be lost to the galaxy over the timescale of the solar system's age. Between 100,000 astronomicznych единиц and the nearest star, Proxima Centauri, at approximately 268,000 astronomicznych единиц, there is a region of space where the Sun's gravity is still weak and the gravity of the nearest stars begins to play a role. Objects in this region, if any exist, would be difficult to assign uniquely to our solar system or to the stellar neighborhood generally. The distinction between our solar system and the interstellar medium is not a sharp boundary. It is a gradual transition that occurs over a range of distances between approximately 100,000 and perhaps 200,000 astronomical units, half a light year to a light year. The solar system does not end, it fades. Now let us think about how the Oort Cloud formed, because understanding its origin illuminates why it is structured the way it is, and why it contains what it contains. The solar system formed approximately 4,6 billion years ago from the collapse of a giant molecular cloud, a cold, dense region of gas and dust within the Milky Way. This collapse produced the Sun at the center and the protoplanetary disk that eventually gave rise to the planets, asteroids, and comets. In the early solar system, the region where the gas giants formed, from approximately 5 to 30 astronomical units from the Sun, was populated with a vast population of planetesimals, kilometre-sized to planet-sized objects made of ice and rock. These were the building blocks of the outer planets, and the material that the outer planets did not incorporate into their bulk remained as a vast population of small icy bodies. As Jupiter and Saturn formed and grew, their gravitational influence began to dominate the outer solar system. The gas giants gravitationally scattered the planetesimals that crossed their orbits, ejecting them onto new trajectories. Many of these scattered planetesimals were thrown onto hyperbolic orbits that ejected them from the solar system entirely, lost to interstellar space. Others were scattered inward and incorporated into the inner planets or the Sun, and a fraction, perhaps a few percent, were scattered onto very elliptical orbits that took them far out into the solar system's outer reaches, into the region we now call the Oort Cloud. The Oort Cloud is, in this sense, the debris field of planetary formation, the material that the forming planets could not incorporate and could not eject entirely, stranded in the outer reaches of the solar system by the gravitational influence of the gas giants. But the process did not stop with the initial scattering. Once in the outer cloud, these objects were subjected to the gravitational influences of passing stars and galactic tides over billions of years. These influences gradually randomized the orbital orientations. Objects that originally had orbits confined to the plane of the solar system were scattered onto randomly oriented orbits in 3 dimensions, producing the roughly spherical structure of the outer Oort cloud we see today. The inner Oort cloud has been less thoroughly randomized. Its disk-like structure reflects the fact that it has been exposed to these external perturbations for shorter times, or that the perturbations are less effective at the smaller distances. This formation process has a specific consequence for the chemical composition of Oort cloud objects. They formed in the outer part of the protoplanetary disk, where temperatures were cold enough for volatile ices to condense: water ice, carbon monoxide ice, carbon dioxide ice, methane ice, ammonia ice. They were then scattered outward without the thermal processing that objects in the inner solar system underwent. They have been preserved in near absolute zero conditions ever since. The Oort cloud is a frozen archive of the early solar system. The material there is the most pristine sample of the molecular cloud from which the Sun and planets formed. When long-period comets arrive from the Oort cloud and astronomers analyze their spectra, they are sampling material that has not been significantly altered since before the Earth existed. This is one of the most compelling scientific arguments for studying comets and for eventually sending missions to the Oort cloud. The material there is a time capsule from the solar system's birth, preserved with extraordinary fidelity for 1733 billion years. Now let us think about the numbers that define the Oort cloud's scale in a different way. Not in astronomical units, which become abstract at these distances, but in comparisons that make the scale viscerally immediate. The distance to the inner edge of the Oort cloud, approximately 2,000 astronometer Eudenics, is piedisat times the distance from the Sun to Pluto's average orbital distance. It is 300 billion kilometers. It is 2,000 times the Earth-Sun distance. Light, travelling at 299,792 kilometers per second, takes approximately 11,5 days to cross this distance. Not 8 minutes, as it does to reach Earth from the Sun, not 4 hours, as it does to reach Neptune, 11,5 days. The mid-range of the Oort cloud, approximately 50 AU, is 1666 times the distance to Pluto, 7,5 triliona kilometrów. Light takes approximately 290 days, almost a full Earth year, to travel from the Sun to this distance. The outer edge of the Oort cloud, approximately 100,000 astronomicznych единиц, is 1,5 1,58 light-years from the Sun. Light takes 1,58 years to travel from the Sun to the Oort Cloud's outer boundary. 1,58 light-years. The nearest star, Proxima Centauri, is 4,24 light-years away. The outer edge of our solar system extends 37% of the way to the nearest star. We do not live in a solar system surrounded by the void of interstellar space on all sides. We live in a solar system that extends 37% of the way to our nearest stellar neighbor. The space between us and Proxima Centauri is not empty. It is filled, for the first percent of the journey, with our own solar system's gravitational domain. Now let us think about what this means for the concept of where one solar system ends and the interstellar medium begins. If our solar system extends light years from the Sun, and Proxima Centauri is light years away, then there is approximately light years of genuine interstellar space between the edge of our solar system and the edge of Proxima Centauri's gravitational domain. But Proxima Centauri also has an Oort cloud, or something equivalent. The gravitational domain of Proxima Centauri extends outward from that star to the point where its gravity is balanced by the galaxy's gravitational influence. For Proxima Centauri, a star with approximately % of the Sun's mass, this distance is somewhat smaller than for our Sun, perhaps to 1 light-year in radius. If Proxima Centauri's gravitational domain extends approximately 0,7 light-years from that star, and our solar system's gravitational domain extends approximately 1.6 light-years from the Sun, then the two gravitational domains are separated by approximately 2 light-years of genuine interstellar space. The gap between solar systems, the true interstellar medium, gravitationally unattached to any specific star, is narrower than the naive picture suggests. It is not 4,24 light-years of interstellar void separating our solar system from the nearest one. It is approximately 2 light-years of interstellar void between the outer reaches of two gravitationally bound stellar systems. And within that 2 light-year gap, there may not be nothing. The galactic environment is not empty between stars. Interstellar gas, interstellar dust, cosmic rays, the magnetic field of the galaxy, these fill the space between stars. And the perturbation history of both solar systems, the objects scattered out of each system over billions of years, may have populated this region with additional icy bodies that have escaped the gravitational attachment to either star. Some researchers have proposed that the Oort clouds of nearby stars may actually overlap, that the outer reaches of our Oort cloud and the outer reaches of the clouds of nearby stars intermingle in the space between solar systems. At the outermost, most tenuously bound fringes of each system, the boundary between one system and another may be genuinely ambiguous. The solar system does not have a clear edge, it has a gradient. A gradual transition from the tightly bound, well-characterized inner solar system to the tenuously bound, poorly understood outer solar system, to the ambiguous edge where our gravitational domain and the gravitational domain of neighboring stars become comparable. Now let us think about what Voyager 1 can tell us about this transition, and what it cannot tell us. Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, at approximately 720 astronomiczej jedynitsa in 12,020. Since then, it has been in what scientists call interstellar space. But this does not mean it has left the solar system in any gravitational sense. At 730 astronomiczej jedynitsa, Voyager 1 is approximately 8% of the way to the inner edge of the Oort cloud. It is approximately 0,16% of the way to the outer edge. In terms of the solar system's full gravitational extent, Voyager 1 has barely left the neighborhood of the Sun. Voyager 1's power source, radioisotope thermoelectric generators running on the decay of plutonium-1231, will cease to produce enough electricity to operate its scientific instruments within the next few years. The spacecraft will continue to travel outward in silence, communicating nothing, carrying nothing, heading in the approximate direction of the constellation Ophiuchus. In approximately 300 years, long after the last instrument has gone silent, long after the last signal has been received from the spacecraft, Voyager 1 will reach the inner edge of the Oort Cloud. It will enter the cloud silently, detecting nothing, transmitting nothing, carrying its golden record and its message for any civilization that might find it, drifting among 2 trillion comet nuclei in the near-perfect darkness and near-perfect cold of the outer solar system. It will take approximately 3,000 years from the current moment for Voyager 1 to exit the other side of the Oort Cloud and enter the genuine interstellar medium. 3,000 years in the Oort Cloud. After short 7 years of travel, Voyager 1 has still not arrived at the structure we are discussing tonight. The Oort Cloud is so far away that our fastest outbound spacecraft has decades of additional travel and then centuries before it reaches even the inner edge. Now let us think carefully about what we actually know about the Oort Cloud and how we know it, because this is a region of the solar system that no spacecraft has ever reached, that no telescope can directly observe, and about which almost all of our knowledge is indirect. We have never seen an Oort Cloud object in the Oort Cloud. None of the 2 trillion objects we believe to be there have been directly imaged or detected at their native distances. They are too far away, too small, too dark, and too cold to be detected by any telescope we have built or plan to build in the foreseeable future. What we know about the Oort Cloud comes from 2 indirect sources: the comets that arrive in the inner solar system and theoretical models of the solar system's formation and evolution. When a comet arrives from the outer solar system, when its orbital parameters, carefully measured over many observations, reveal a period of millions of years and an aphelion in the outer solar system, it is identified as an Oort Cloud comet. By characterizing many such comets, their compositions, their orbital characteristics, their arrival directions, astronomers piece together an indirect picture of the cloud they came from. The arrival directions of long-period comets are nearly isotropic. They come from all directions in the sky, not preferentially from the plane of the solar system. This is the primary observational evidence for the Oort Cloud's roughly spherical structure. If the comets came from a flat disk, like the Kuiper belt, they would preferentially arrive from the plane of the solar system. The distribution of orbital energies of long-period comets constrains the distribution of orbital energies in the Oort Cloud itself, providing information about the cloud's density as a function of distance from the Sun. The chemical compositions of Oort Cloud comets, measured from the gases they release when heated by the Sun as they approach perihelion, provide information about the chemical conditions in the outer solar system at the time of the cloud's formation. And theoretical models of the solar system's formation, models that start from the initial conditions of the protoplanetary disk and follow the gravitational dynamics over billions of years, predict the properties of the Oort Cloud based on what we know about the planets and the galactic environment. These models are constrained by the observed properties of long-period comets and refined to match the observations. The picture that emerges from this indirect reconstruction is the Oort Cloud as we have described it. 2 trilliona objects, extending from 2000 to 100,000 AU, with an inner disk-like component and an outer spherical shell, formed from the scattering of planetesimals by the forming gas giants. But the picture has significant uncertainties. The total number of objects, 2 trilliona, could be off by a factor of several in either direction. The inner-outer structure of the cloud is less well constrained than the outer spherical shell. The detailed density profile, how the number density of objects changes with distance from the Sun, is poorly known. And there may be structures within the cloud, overdense regions, fossil signatures of the cloud's formation history that we have no way to detect with current methods. The Oort Cloud is the least well-characterized major structure of the solar system. We know it is there. We know its approximate extent. We know its approximate population. Everything else is inference, model, and educated guess. Now let us think about the most important thing the Oort Cloud tells us about the solar system's relationship with the rest of the galaxy. Because the Oort Cloud is not just a distant reservoir of comets, it is the interface between the solar system and the galactic environment. At the distances of the Oort Cloud, the Sun's gravity is so weak that the orbits of objects are easily perturbed by external gravitational influences. The galactic tide, the variation in the galaxy's gravitational field across the extent of the solar system, applies a force that, while negligible in the inner solar system, becomes significant in the Oort Cloud. The galactic tide operates continuously, acting on Oort Cloud objects over millions of years, slowly changing their orbits. For objects in the outer Oort Cloud, the galactic tide is the primary mechanism by which orbits are modified over time. It is more effective than occasional stellar passages at driving the long-term evolution of the cloud. Stellar passages, encounters with other stars that pass within a few light-years of the Sun, occur on timescales of hundreds of thousands to millions of years. When a star passes close enough, its gravity temporarily distorts the orbits of Oort Cloud objects, potentially sending some of them on trajectories that bring them into the inner solar system. The specific history of stellar passages near the Sun over the past few 100 million years is reflected, in principle, in the current rate of long-period comet arrival, bursts of comets corresponding to close stellar passages. The solar system's orbit around the Milky Way, a roughly circular orbit in the galactic disk with a period of approximately 225 to 230 million years, takes it through regions of varying stellar density and varying molecular cloud density. When the solar system passes through a denser region of the galactic disk, particularly when it passes through or near a spiral arm, where stars and gas are more concentrated, the rate of stellar passages near the Sun increases, and the Oort Cloud is perturbed more intensely. Some researchers have proposed that periodic bursts of comet activity, possibly correlated with periods of elevated impact rate on Earth, correspond to the solar system's passages through dense regions of the galactic disk. The evidence for this correlation is debated, but the mechanism is physically sound. The galactic environment drives the delivery of Oort Cloud comets to the inner solar system, and the galactic environment changes periodically as the Sun orbits the galaxy. This means that the Oort Cloud connects the solar system to the galactic environment in a specific and physical way. Events that happen far from the solar system, stellar passages, molecular cloud encounters, the solar system's traversal of the galactic spiral arms, have direct consequences for the delivery of comets to the inner solar system, and potentially for the rate of impacts on Earth and the other planets. The Earth's history, its cratering record, possibly its mass extinction record, is connected to the solar system's galactic environment through the Oort Cloud. The Oort Cloud is the mechanism by which galactic processes leave their mark on the inner solar system. Now let us think about what long-period comets look like when they arrive, because these are our only direct samples of Oort Cloud material, and what they tell us is extraordinary. When an Oort Cloud object is perturbed onto an inward trajectory, it begins a journey that may take millions or even tens of millions of years. Falling from thousands of astronomical units, the object accelerates slowly under the Sun's gravity, picking up speed as it approaches. In the outer solar system, it is dark, cold, inert, indistinguishable from any other icy rock. As it crosses into the region of the giant planets, astronomical units from the Sun, the heat from the Sun begins to have an effect. Volatile ices near the surface start to sublimate, to transition directly from solid to gas, releasing trapped gases and dust particles. The comet begins to develop its coma, the atmosphere of gas and dust that surrounds the nucleus when it is active. As it continues inward, the activity intensifies. The solar wind pushes the gas and dust of the coma away from the Sun, forming the comet's characteristic tail, always pointing away from the Sun regardless of the direction of the comet's travel. A bright comet can develop a tail millions of kilometers long. The spectroscopy of the coma, the chemical analysis of the gases being released, provides the most direct information we have about the composition of Oort Cloud material. The gases detected include water vapor, carbon monoxide, carbon dioxide, methane, ammonia, hydrogen cyanide, and dozens of complex organic molecules. Some of these molecules, amino acid precursors, sugars, alcohols, are the kinds of organic compounds that might have played a role in the origin of life on Earth. This is one of the most scientifically significant aspects of comet chemistry. The comets that have bombarded the inner solar system over its history, and the Oort Cloud comets among them, delivered organic molecules to the early Earth. They may have brought water, they may have brought the chemical precursors of life. The same material that is frozen in the Oort Cloud right now, preserved for 4,6 billion years, may have contributed to the conditions that made life on Earth possible. The Oort Cloud is not just a curiosity at the edge of the solar system, it is potentially connected to the origin of life on Earth through the chemistry of long-period comets. Now let us think about a specific and underappreciated aspect of the Oort Cloud, the Sedna problem, and what Sedna tells us about the solar system's history. Sedna is a trans-Neptunian object discovered in 2003. Its orbit is extraordinary by any measure of the solar system's known population. Sedna's perihelion, the closest point of its orbit to the Sun, is approximately 76 astronomicznych jedinic. This is well beyond Neptune, well beyond the Kuiper belt, and even somewhat beyond the scattered disk. At perihelion, Sedna is 76 times the Earth-Sun distance, 2.5 times the distance to Pluto. Sedna's aphelion, its farthest point from the Sun, is approximately 937 astronomicznych jedinic, nearly 1,000 astronomicznych jedinic. In units more meaningful at this scale, approximately 1/100 of a light year. Sedna's orbital period, the time for one complete orbit around the Sun, is approximately 11,400 years. What makes Sedna scientifically extraordinary is not its distance, but its perihelion. At 76 astronomical units, Sedna's closest approach to the Sun is far beyond the reach of Neptune's gravitational influence. Neptune is at 30 astronomical units, too distant to have significantly perturbed an object at 76 astronomical units into its current orbit. The scattered disk, which extends to approximately 100 astronomicznych jedinic in perihelion, is produced by gravitational scattering by Neptune. But Sedna's perihelion is too far from Neptune to have been placed there by Neptune's current gravitational influence. How did Sedna get its orbit? The most compelling explanation: something else perturbed Sedna, some gravitational influence that is no longer operating, or operates too rarely to have been detected. The leading candidate, a close stellar encounter in the early solar system. When the Sun was young, it was likely surrounded by other stars, born in the same stellar nursery, a star cluster that has since dispersed as the cluster members drifted apart over billions of years. During the first few 100 million years of the solar system's existence, when the Sun was still embedded in its birth cluster, close encounters with neighboring stars were much more frequent than they are today. Such an encounter, a star passing within a fraction of a light-year of the young Sun, could have gravitationally perturbed the orbits of objects in the outer solar system, pushing some into the high perihelion orbits like Sedna's. As the star cluster dispersed and the neighbouring stars moved away over billions of years, the perturbation mechanism was removed, leaving Sedna stranded in its high perihelion orbit with no current mechanism to explain how it got there. This hypothesis, that Sedna records the signature of the Sun's birth cluster, is one of the most tantalizing ideas in planetary science. It suggests that the outer solar system carries a fossil record of the environment in which the solar system formed, encoded in the orbits of objects like Sedna. But Sedna is not unique. A second object with a similar high perihelion orbit, VP 113, nicknamed Biden by its discoverers, who noted the VP in the designation, was discovered in 2020 with a perihelion of approximately 20 AU. Other Sedna-like objects, with perihelia too large to be explained by Neptune's current gravitational influence, are suspected to exist in significant numbers. The population of Sedna-like objects, the so-called inner Oort Cloud objects, or sednoids, may be the inner Oort Cloud itself, the disk-like structure of objects that formed in the early solar system and were perturbed to their current orbits by the birth cluster environment. If this is correct, Sedna is not just a curiosity. It is a window into the solar system's birth environment, a fossil object whose orbit was set by conditions that existed billion years ago, when the Sun was young and embedded in its birth cluster, and which has been preserved in this high perihelion orbit because no subsequent process has been able to move it significantly. The inner Oort Cloud may be full of objects like Sedna. We have found two. Current surveys can only detect them at or near perihelion, when they are closest to Earth and brightest. The vast majority of their orbits, % or more of the time, they are too far away to be detected with current instruments. The Oort Cloud, inner and outer, is largely invisible to us. We are inferring its properties from the rare glimpses we get of the objects that happen to come close. Now let us think about the implications of the Oort Cloud for the question of what lies beyond our solar system, and what the distribution of Oort clouds around nearby stars means for the interstellar medium. If our Sun has an Oort cloud extending to approximately 1.6 light-years, it is reasonable to assume that other stars have similar structures. The process that formed our Oort cloud, gravitational scattering of planetesimals by gas giants during the formation of a planetary system, is expected to occur in any planetary system with giant planets, and giant planets appear to be common. The nearest stars to our Sun, the stars within approximately light-years, are likely to each have their own Oort clouds, if they have planetary systems with giant planets. These clouds would extend outward from each star to distances comparable to our own Oort cloud. For stars separated by chapter light-years, the separation between our Sun and Proxima Centauri, the Oort clouds of the two stars do not overlap, but they are not enormously far apart. The gap between the outer edge of our Oort cloud and the outer edge of Proxima Centauri's Oort cloud might be as small as 1 to 1.5 light-years. For stars in denser stellar environments, in the cores of open clusters, or in the galactic bulge where stars are more closely packed, the Oort clouds of neighbouring stars might actually overlap. Interactions between the Oort clouds of different stars would be possible. Material from one star's Oort cloud could be captured by another star. Interstellar comets, objects ejected from the Oort cloud of one star and captured by the gravity of another, might be more common than interstellar space suggests. The detection of Odin I/Oumuamua in 2017, the first confirmed interstellar object to pass through our solar system, provided direct evidence that material does travel between stellar systems. Oumuamua arrived from outside our solar system, moving at a velocity inconsistent with gravitational capture by the Sun, and was likely ejected from another star's system. Whether it originated from an Oort cloud or from a different part of another stellar system is uncertain, but its existence confirms that the population of interstellar objects, material drifting between stars, is real. The second confirmed interstellar object, 2I/Borisov, detected in 2019, had a clearly cometary nature. It showed the gas and dust release characteristic of a comet as it approached the Sun. This suggests it originated in the cold outer regions of another stellar system, possibly an analogue of our Oort Cloud. These detections, two interstellar objects in the few years since our survey capabilities became adequate to detect them, suggest that the population of interstellar objects passing through our solar system is large. Estimates from the detection statistics suggest that at any given time there may be one or a few interstellar objects within the orbit of Neptune and many more in the outer solar system. The interstellar medium is not empty of material from stellar systems. It is populated, sparsely but definitely, with objects from Oort clouds across the galaxy. Stars shed material into interstellar space as their Oort clouds are perturbed by galactic processes, and this material drifts between stars, occasionally passing through other stellar systems. The galaxy is an ecosystem in which material is not permanently confined to individual stellar systems, but circulates, slowly, over billions of years, through the interstellar medium from one system to another. This is a profoundly different picture of the interstellar medium than the simple void between stars narrative. The space between stars is not simply empty. It is threaded with the shed debris of billions of planetary systems, the discarded inventory of Oort clouds accumulated over the galaxy's history. Now let us think about what a mission to the Oort cloud would look like, not as an exercise in current engineering limits, but as a way of understanding what we would learn if we could go. The Oort cloud is the most scientifically valuable and least accessible region of the solar system. It contains the most pristine material from the solar system's formation, preserved in conditions that have barely changed in shed billion years. Visiting an Oort cloud object would be like collecting a sample from the solar system's birth. Chemistry untouched by the geological and thermal processing that has altered all other solar system material we have accessed. The first challenge is simply getting there. At 2000 astronomicznych jedinic to the inner edge, even the fastest spacecraft we could build today would take centuries to arrive. The New Horizons spacecraft, which flew past Pluto in 2015 and has been heading outward since, is travelling at approximately 14 km w sekundę. At this speed, it would take approximately 4700 years to reach the inner edge of the Oort cloud. For a mission to be useful on human timescales, a spacecraft would need to travel at velocities of hundreds to thousands of kilometers per second, factors of 10 to 100 faster than our fastest current spacecraft. This is within the realm of theoretical propulsion concepts: nuclear pulse propulsion, laser sail propulsion, nuclear thermal propulsion with multi-stage designs, but far beyond anything that has been built or tested. Assuming a future spacecraft could be accelerated to, say, 100 km w sekundę, roughly 6 times the speed of Voyager Odin, it would reach the inner edge of the Oort cloud in approximately 190 years. Still a multi-generational project by any human standard, but conceivable as a long-term civilizational commitment. What would such a mission find? First, direct detection of Oort cloud objects at their native distances. Currently, we can only detect Oort cloud objects when they are perturbed into the inner solar system and come close enough to be bright enough to observe. A spacecraft in the Oort cloud could detect objects with instruments sensitive enough to find dark, cold bodies at their home distances. The first survey of the Oort cloud population, the actual count and distribution of objects, would be revolutionary. Second, chemical analysis of Oort cloud material without the thermal processing of sunlight. Long-period comets give us a glimpse of Oort cloud chemistry, but this glimpse is filtered through the comet's activity close to the Sun, the heating, sublimation and outgassing that alters and exposes different layers of the nucleus. An in situ sample of an Oort cloud object at its native distance would be a pristine snapshot of the solar system's primordial chemistry. Third, the opportunity to directly sample interstellar material in the region where the solar system's gravitational influence fades. The outer Oort cloud is the transition zone between our solar system and the interstellar medium. A spacecraft there would be in the ideal location to measure the properties of the interstellar medium at the boundary of our gravitational domain, the density, temperature, composition, and magnetic field of the material that surrounds our solar system. Fourth, detection of any unexpected structures.
The Oort cloud, as a region we have never directly explored, may contain surprises that no theoretical model has predicted. The history of solar system exploration, from the discovery of Saturn's complex ring structure to the detection of Pluto's heart-shaped nitrogen glacier, from the geysers of Enceladus to the organic chemistry of Titan's atmosphere, is a history of surprises. The Oort cloud, visited for the first time, would almost certainly offer its own. Now let us think about what the Oort cloud means for the longest arcs of solar system history, for the question of how the solar system will change over the billions of years to come. The Sun is currently in the middle of its main sequence lifetime. It has approximately 1 billion years of hydrogen fusion remaining in its core before it will expand into a red giant, engulf the inner planets, and eventually shed its outer layers as a planetary nebula, while its core contracts to a white dwarf.
The Oort cloud will not be destroyed in this process, or at least most of it will not. The expansion of the Sun into a red giant will dramatically increase the luminosity and the stellar wind, which will push the heliopause outward and potentially ablate the surfaces of Oort cloud objects that come close during this phase. But the vast majority of the Oort cloud, the 2 trillion objects at 2,000 to 100,000 astronomical units, will be largely unaffected by the Sun's evolution. They will continue to orbit the white dwarf that succeeds the Sun in the same orbits they currently occupy. The white dwarf that the Sun will become will be a dim, cooling cinder, producing no significant luminosity compared to the current Sun. The Oort cloud objects orbiting it will be in near absolute zero conditions, even colder than today. They will continue to be perturbed by galactic tides and stellar passages, occasionally being sent on trajectories that bring them close to the white dwarf, comets arriving at a dead star with no heat to activate them, drifting in silence past a cooling ember. The Oort cloud will outlast the Sun as a luminous star by billions of years. It will outlast the planetary system as we know it. The Sun's evolution will dramatically alter the inner solar system, but the Oort cloud will persist. It will be there when the last light from the dying Sun fades, and it will continue orbiting the cold white dwarf for billions of years after. In this sense, the Oort cloud is not just the outer boundary of the current solar system, it is the most durable part of the solar system, the part that will persist longest into the deep future. The Earth, the inner planets, even the gas giants may be significantly altered or destroyed over the Sun's evolution. The Oort cloud will endure. Now let us think about what all of this means for the picture of the solar system that you carry in your mind, because the Oort cloud should fundamentally change that picture. The solar system, as you probably picture it, 8 planets in a flat disk, the Sun at the center, everything well lit and well characterized, a clear boundary somewhere around Neptune. The solar system as it actually is, a flattened disk of planets, extending to Kuiper belt and scattered disk extending to roughly 1,000 astronomical units, the heliosphere extending to approximately 120 astronomical units, and then the vast majority of the solar system's volume, the Oort cloud, a roughly spherical structure extending from 2,000 to 100,000 astronomical units, containing 2 trillion objects, preserved at near absolute zero temperatures, perturbed by galactic tides and stellar passages, occasionally sending comets into the inner solar system as the only evidence of its existence. The volume of the Oort cloud, relative to the volume of the inner solar system enclosed by Neptune's orbit, is extraordinary. Neptune's orbit encloses a sphere of radius 3 astronomicznych jedynic, volume 4/3 pi umnożyć na 30 w stепени 3 astronomicznych jedynic w stепени 3 примерно равно 113 000 кубических astronomicznych jedynic. The Oort Cloud, treated as a spherical shell from 2000 to 100 000 astronomicznych jedynic, has a volume of approximately 4/3 pi умножить на 100 000 в степени 3 минус 2000 в степени 3 астрономических единиц в степени 3 примерно равно 4,19 умножить на 10 в степени 15 кубических астрономических единиц. The Oort Cloud has approximately 37 миллиардов times the volume of the planetary solar system enclosed by Neptune's orbit. The solar system that your mental picture includes, the planetary solar system, Neptune, and inward, represents approximately 1 in 37 billion of the actual volume of the solar system. Your mental picture of the solar system contains approximately 0.000000003% of the actual solar system by volume. The other 99,999,999,999% is the Oort Cloud. This is not a minor correction to your picture. It is a replacement of your picture with something categorically different. The solar system is not the planetary disk with a bit of scattered debris beyond. It is an enormous, nearly spherical structure extending halfway to the nearest star, of which the planetary disk is a tiny central core, a grain of sand in a beach. We live in the grain of sand. The beach is the Oort Cloud, and the beach extends in every direction almost to the nearest star. Let us now think about something that gives the Oort Cloud a specific and rarely discussed significance. The question of what the Oort Cloud means for the concept of the solar system as a gravitationally coherent structure, and what defines the boundary between belonging to our solar system and belonging to the galaxy. The question sounds philosophical, but it has a physical answer, and the answer is more complex and more interesting than any simple boundary line. Gravity is the force that binds the solar system. Every object in the solar system, every planet, every asteroid, every comet, every Kuiper belt object, every Oort Cloud comet, is in the gravitational grip of the Sun. The Sun's mass, approximately umnożyć na 10 w 30 stепени kilograms, constituting 99,86% of all the mass in the solar system, dominates the gravitational dynamics of everything within the solar system's bounds. But the Sun is not the only gravitational influence in the universe. The Milky Way galaxy contains approximately 200 to 400 billion other stars, plus an enormous amount of dark matter, plus interstellar gas and dust. All of this mass generates a gravitational field, not a simple field pointing in one direction, but a complex, spatially varying field that permeates the entire galaxy. For an object close to the Sun, within the planetary system, within a few hundred astronomical units, the Sun's gravity dominates completely. The galactic gravitational field is present, but negligible compared to the Sun's pull. An asteroid at 2 astronomical units is approximately 10 to the power of 6 times more strongly bound to the Sun than it is influenced by the galactic field. For an object far from the Sun, at 50,000 astronomical units, in the middle of the Oort Cloud, the situation is different. The Sun's gravity at this distance is approximately 2.5 billion times weaker than at Earth's distance. The galactic gravitational field, while still weaker than the Sun's at most Oort Cloud distances, is no longer completely negligible. It is the dominant perturbation force. At some specific distance from the Sun, the boundary of the solar system in a precise gravitational sense, the galactic tidal force equals the Sun's gravitational force. This is the Hill sphere of the Sun within the galaxy, the region within which the Sun's gravity dominates over the galaxy's tidal force.
The radius of the Sun's Hill sphere in the galactic context is approximately 1 to 2 light-years, or 63 tysici to 126 tysic AU. This corresponds closely to the estimated outer extent of the Oort Cloud. This is not a coincidence. The Oort Cloud extends to approximately the limit of the Sun's gravitational dominance because objects beyond this limit cannot remain stably bound to the Sun. Any object placed beyond the Hill sphere would be tidally stripped by the galaxy, pulled away from the Sun by the differential gravitational force of the galaxy, and eventually captured by the galactic potential rather than the solar potential. The Oort Cloud occupies the region where the Sun's gravity is still dominant, but only barely, where orbits are stable over billions of years but vulnerable to perturbation, where the galactic environment has its most direct influence on the solar system. This means the Oort Cloud is not simply the outer edge of the solar system. It is the zone of transition between the solar system and the galaxy, the region where the two gravitational regimes compete, where material can be shared between a star and the broader galactic environment, and where the solar system's history is most directly connected to its galactic context. Now let us think about the specific ways the galactic tide affects the Oort Cloud, because the galactic tide is not a static force, but a dynamical influence that changes as the Sun orbits the galaxy. The galactic tide, the tidal force produced by the galaxy's gravitational field, has two components. The vertical component acts perpendicular to the plane of the galactic disk, compressing material toward the plane on a timescale of tens of millions of years. The radial component acts in the plane of the disk, pushing material outward from the galactic center on one side of an orbit and inward on the other. For Oort Cloud objects, the vertical tidal force is particularly important. It creates a torque on the orbits of Oort Cloud objects, a force that changes the orientation of their orbital planes. For objects in orbits that are inclined to the galactic plane, the vertical tide changes the orbital inclination over time, cycling the orbit through different orientations on timescales of tens to hundreds of millions of years. This cycling of orbital inclinations has a specific consequence. As an Oort Cloud object's orbital inclination changes under the galactic tide, its perihelion distance, the closest point of its orbit to the Sun, also changes. Objects whose perihelia start at distances of thousands of astronomical units may, over millions of years of tidal evolution, find their perihelia reduced to values within the planetary system. When this happens, the object becomes a comet, entering the inner solar system, being heated by the Sun, developing a coma and tail. The galactic tide is therefore one of the primary mechanisms by which the Oort Cloud delivers comets to the inner solar system. It is not random chance that determines which Oort Cloud objects become comets. It is the systematic, deterministic influence of the galactic tidal field acting on orbits over millions of years. This connection between the galactic tide and comet delivery has a specific consequence. The rate of comet delivery from the Oort Cloud is not constant over time. It varies as the solar system moves through the galaxy and encounters different regions of the galactic gravitational field. The solar system's orbit around the galaxy is not perfectly circular and not confined to the galactic midplane. It oscillates above and below the galactic plane with a period of approximately 350 million years, like a sinusoidal wave superimposed on its roughly circular orbit. As the solar system moves toward the galactic plane, it passes through denser regions of the galactic disk, where the stellar density and gas density are higher, and the gravitational perturbations on the Oort Cloud are stronger. This oscillation has been proposed as the explanation for an apparent periodicity in the terrestrial impact record.
a suggestion, controversial but physically motivated, that mass extinctions on Earth occur with a periodicity of approximately 26 to 30 million years, corresponding to the solar system's oscillation through the galactic plane. Each time the solar system passes through the densest part of the galactic disk, each time it crosses the galactic midplane, the Oort cloud is more strongly perturbed, delivering more comets to the inner solar system and increasing the probability of a large impact on Earth. Whether this periodicity in the impact record is real and whether it is caused by the galactic plane oscillation is not established. The geological record of mass extinctions is complex, the dating uncertain, and the proposed periodicity sits at the edge of statistical significance. But the mechanism is sound. The solar system's galactic orbit modulates the rate of Oort cloud perturbation, which modulates the comet flux, which modulates the impact rate. If this mechanism is correct, the history of life on Earth is connected, through the Oort cloud, to the solar system's position in the galaxy. The galactic environment has directly influenced the evolution of life on our planet through the occasional delivery of large impactors from the Oort cloud. The Oort cloud is not just the outer boundary of the solar system, it is the interface through which the galactic environment has repeatedly altered the history of life on Earth. Now let us think about something specific and under-discussed: the potential for the Oort cloud to contain objects more exotic than simple comet nuclei.
The Oort cloud formed primarily from the scattering of icy planetesimals during the formation of the gas giants. These planetesimals were the building blocks of the outer solar system, objects a few kilometers to a few hundred kilometers in size, made of ice and rock. But the Oort cloud may also contain objects that were not originally part of our solar system. During the Sun's early history in its birth cluster, close encounters with neighboring stars could have transferred material between stellar systems. Objects that were weakly bound to a neighboring star, outer Oort cloud analogues of a neighboring system, could have been perturbed by the gravitational influence of our Sun and captured into our Oort cloud. If this happened, and theoretical models suggest it is likely to have occurred during the Sun's time in its birth cluster, then the Oort cloud contains material from other stellar systems. Comets that arrive in our inner solar system from the outer Oort cloud may, in some cases, have originated around a different star. This is not a remote theoretical possibility, it is a likely consequence of the solar system's birth environment and the mechanics of gravitational capture during close stellar encounters. The Oort cloud is probably a mix of native material, objects scattered outward from our own protoplanetary disk, and captured material from neighboring stellar systems. This makes the Oort cloud even more scientifically valuable than it would be if it contained only native material. It is potentially a repository of samples from multiple stellar systems, preserved in their pristine state for billions of years. We have no way, with current knowledge, to distinguish a native Oort cloud object from a captured one. The chemical composition of captured material might be different from native material, reflecting the different protoplanetary disk chemistry of the parent star. But these differences might be subtle and would require very detailed analysis to detect. Future missions to the Oort cloud, if they can return samples, might be able to identify captured extrasolar material by its isotopic composition, the specific ratios of different isotopes of the same element that are fingerprints of the nuclear processes in different stars and the conditions in different protoplanetary disks. This possibility, that the Oort cloud contains samples from other stellar systems, means that a mission to the Oort cloud is not just a mission to the outer solar system, it is potentially a mission to the stars. Without leaving our gravitational domain, we might be able to obtain and analyze material from other stellar systems, learning about the conditions in other protoplanetary disks and the chemical histories of other stars. Now let us think about the Oort cloud in the context of the solar system's entire history, not just how it formed, but how it has changed over 22 billion years. The Oort cloud, as it exists today, is not the same as the Oort cloud that formed 22 billion years ago. It has been continuously losing objects objects perturbed into the inner solar system, where they are eventually ejected or destroyed, objects stripped by stellar passages and galactic tides that reduce their binding to the Sun below the threshold for retention. The original Oort Cloud, the population of objects immediately after it formed from the scattered planetesimals of the protoplanetary disk, may have been much more populous than the current cloud. Estimates suggest that the total mass in the original Oort Cloud may have been comparable to several Earth masses, tens to hundreds of times the mass currently estimated to be in the cloud. Of 1 billion years, approximately 20% to 20% of the original Oort Cloud population may have been lost. Objects were perturbed into the inner solar system and destroyed, either by impacts on planets, by being ejected from the solar system entirely during close approaches to the giant planets, or by solar heating that eventually evaporated their volatile ices. Objects at the very outer edge of the cloud were stripped by the galactic environment. Objects in the inner cloud were perturbed by the gas giants during the dynamic early history of the solar system. What remains today, the 2 trillion objects of the current Oort Cloud, is the surviving remnant of a much larger original population. It has been depleted by 4.6 billion years of loss processes. This depletion history has implications for the rate of comets being delivered to the inner solar system. In the early solar system, the first billion years, the Oort Cloud was much more heavily populated, and the rate of comet delivery was much higher. The late heavy bombardment, the period of intense impact activity on the inner planets approximately 2 billion years ago, may have been partly driven by comets from the Oort Cloud as well as asteroids from the main belt. As the Oort Cloud has been depleted over billions of years, the comet flux to the inner solar system has diminished. The current rate of long-period comet arrivals, a few per year to the inner solar system, is much lower than the rate in the early solar system. This has a specific consequence for Earth's history. The delivery of organic molecules and water by comets, a process that may have contributed to the conditions for life's origin on Earth, was much more intense in the early solar system, when the Oort Cloud was more populated. As the Oort Cloud was depleted, this delivery rate decreased. The early Earth received more cometary material than the current Earth, both because the Oort Cloud was more populated and because the impact probability was higher in the denser early inner solar system. Now let us think about what happens to the Oort Cloud in the very long future, beyond the death of the Sun. When the Sun exhausts its hydrogen fuel in approximately 10 billion years, it will evolve through the red giant phase, losing a significant fraction of its mass through stellar winds. This mass loss will weaken the Sun's gravitational grip on the Oort Cloud. Objects that are currently just barely bound to the Sun will become unbound as the Sun loses mass, drifting away into interstellar space. The outer Oort Cloud, the most tenuously bound region, will be the most affected. As the Sun loses mass, the Hill sphere shrinks. Objects in the outer Oort Cloud that are currently just within the boundary will find themselves outside the new, smaller Hill sphere and will drift away. After the red giant phase, the Sun will shed its outer layers as a planetary nebula, leaving behind a white dwarf with approximately half the Sun's current mass. The sudden mass loss in the planetary nebula phase, occurring on timescales of thousands to tens of thousands of years, will further weaken the gravitational grip of the stellar remnant. A significant fraction of the remaining Oort Cloud may be shed into interstellar space at this stage. What remains, the Oort Cloud of the white dwarf Sun, will be a smaller, more tightly bound version of the current cloud, orbiting a dim, cooling stellar remnant. These objects will continue to be perturbed by galactic tides and stellar passages, occasionally falling toward the white dwarf as comets. But without the heat of a luminous star, these comets will not develop comas and tails. They will simply fall through the inner solar system, dark and cold, unchanged by the encounter. The Oort Cloud will outlast the Sun's luminous phase by billions of years. Long after the last light fades from the white dwarf, the Oort Cloud objects will continue to orbit, slower now, in larger orbits around a dimmer gravitational center, gradually losing members to galactic perturbations, slowly thinning over the billions of years of the white dwarf's cooling. Eventually, over timescales of trillions of years, the Oort Cloud will be entirely dispersed. Galactic perturbations, acting continuously over vast timescales, will remove the last gravitationally bound objects from the white dwarf's domain. The solar system, or what remains of it by then, will finally, truly end. Not with a dramatic event, but with the gradual loss of the last tenuously bound ice balls to the galactic background. Now let us think about what the Oort Cloud means for our understanding of how unique or typical our solar system is. The formation of the Oort Cloud requires specific conditions. It requires a planetary system with gas giants, Jupiter analog planets, capable of scattering planetesimals onto highly eccentric orbits. It requires the solar system to have spent time in a stellar birth cluster, where the galactic environment was dense enough to randomize the orbital inclinations of the scattered objects and create the roughly spherical outer Oort Cloud. And it requires enough time for the Oort Cloud to be populated, evolved, and partially depleted.
All three of these conditions appear to be common in the universe. Giant planets are found around a significant fraction of Sun-like stars. Stars are born in clusters. Essentially all stars, including our Sun, form in clusters before dispersing over tens to hundreds of millions of years. And the age of most stellar systems is comparable to or older than our solar system, providing ample time for Oort Cloud formation. If these conditions are common, then Oort Cloud formation should be common. Most planetary systems with gas giants, a population that may include the majority of Sun-like stars in the galaxy, should have Oort Clouds. This has a specific implication for the galactic environment. The interstellar medium is probably permeated by material shed from the Oort Clouds of billions of stellar systems. Comet nuclei drifting between stars, occasionally passing through other stellar systems, potentially being captured. Oumuamua and Borisov were the first confirmed examples of this population, but they represent only the most recently detected members of what may be an enormous population of interstellar objects, the accumulated output of billions of Oort Clouds over billions of years of galactic history. The space between stars is probably not nearly as empty of material as the interstellar medium's gas density suggests. It is threaded with the cometary debris of countless stellar systems, a slow-moving, cold, dark population of ice and rock drifting between the stars. Our solar system, as it orbits the galaxy, moves through this population continuously. Interstellar objects pass through our solar system regularly. DESI estimates, based on the detection rate, suggest that perhaps one interstellar object larger than 7 meters enters the inner solar system each year. Most of these are too faint to be detected with current instrumentation.
The two we have detected, Oumuamua and Borisov, are likely the tip of an enormous iceberg. This means that the solar system is not isolated. It is permeable, regularly receiving material from other stellar systems, regularly shedding material to the interstellar medium. The boundary between our solar system and the galaxy is not a wall but a membrane, a gradient of gravitational influence through which material passes continuously in both directions. Now let us think about what this means for one of the most profound questions in astrobiology: the question of whether life could be distributed between stellar systems through cometary material. The panspermia hypothesis proposes that life, or the chemical precursors of life, can be distributed between stellar systems by comets, asteroids, or other small bodies. The most common version of this hypothesis involves material ejected from one planetary system by an impact, drifting through interstellar space and eventually landing on a planet in another stellar system. The Oort Cloud is relevant to this hypothesis in a specific way. If comets from the Oort Cloud carry organic molecules, and they do, as spectroscopy confirms, then any comet ejected from our solar system by a stellar perturbation carries with it a payload of complex organic chemistry. If some of these comets are captured by other stellar systems, they deliver this chemistry to those systems. Whether living organisms can survive the journey, the millions of years in interstellar space exposed to cosmic radiation in near absolute zero conditions, is a profound open question. Laboratory experiments have shown that some microbial spores can survive extreme conditions for limited periods.
Whether any form of life could survive millions of years in interstellar space is not established and may not be testable with current science. But the chemical precursors of life, the organic molecules that comets carry, are more robust than life itself. Amino acids, nuclear bases, sugars, alcohols, these have been detected in meteorites that have spent billions of years in space, and they survive the conditions of interplanetary and potentially interstellar travel. If comets exchange material between stellar systems, and the detection of Oumuamua and Borisov establishes that this exchange occurs, then the chemical building blocks of life may be distributed throughout the galaxy through the Oort Cloud network. Each stellar system that has comets is connected to every other stellar system through this network of slow-moving, cold, organic-rich projectiles drifting between stars. The implications for the origin of life are profound.
Earth's oceans and organic chemistry may have been seeded partly by material from other stellar systems, delivered by captured interstellar comets. The specific mix of organic molecules on the early Earth may reflect not just the chemistry of our own Oort Cloud, but the chemistry of multiple other stellar systems whose cometary debris happened to arrive at Earth during its formation period. Life on Earth, if this is true, may have cosmic parents, chemical contributions from stellar systems that no longer exist in the form they had when the chemistry arrived, from stars that have since evolved and died, from protoplanetary disks that condensed billions of years before our Sun ignited. The Oort Cloud is the mechanism through which this cosmic chemistry exchange operates in our solar system. Understanding it is understanding not just the solar system's history, but potentially the history of life's building blocks across the galaxy. Now let us think about the specific numbers that define the Oort Cloud's place in the galaxy. The comparison between the Oort Cloud's scale and the scale of the galaxy itself. The Milky Way's disk has a diameter of approximately 7,000 light-years. The Oort Cloud has a radius of approximately 1,58 light-years. The ratio of the Milky Way's radius to the Oort Cloud's radius is approximately 50,000 to 1.58, about 31,600. In other words, the Oort Cloud, which is an enormous structure by any solar system standard, is approximately 1,31,600 dolia of the Milky Way's disk radius. If you represented the Milky Way as a disk 1 kilometer in diameter, the Oort Cloud of our solar system would be a sphere approximately 3 centimeters in radius, centered at the Sun's location. 3 centimeters. In a disk 1 kilometer across. The Oort Cloud, which extends halfway to the nearest star, which contains trilliona objects, which defines the outermost reach of the solar system, which took Voyager 30 years to enter, even at our fastest achieved velocity, is 3 centimeters in radius on a disk 1 kilometer wide. Every Oort Cloud in every stellar system in the Milky Way would be a 3 centimeter sphere, each one separated from its neighbors by meters to tens of meters on the same scale. 200 to 400 billion of these tiny spheres scattered across a 1 kilometer disk, most of them separated by distances of a few meters at the scale of this comparison. The stars are not as isolated from each other as they appear from within any one Oort Cloud. At the galactic scale, stars are close enough together that the outermost reaches of their gravitational domains are separated by relatively small gaps. The galaxy is a community of overlapping gravitational domains, each one a stellar system with its Oort Cloud. The Oort Clouds separated by distances comparable to the Oort Cloud's own radii.
The interstellar void that seems so absolute from within the solar system, the 4,24 light-years to Proxima Centauri that no spacecraft has come close to bridging, is, at the galactic scale, the gap between adjacent 3-centimeter spheres on a 1-kilometer disk. Not nothing, but not the absolute barrier that it seems from within. This is the perspective the Oort Cloud gives on the galaxy, a perspective in which the solar system is one of many. The boundaries between them are gradual rather than sharp. The material flowing between them is real and continuous, and the isolation of any one stellar system from the others is less absolute than it appears from the inside.
Now let us think about what happens at the specific moment when a long-period comet, an Oort Cloud object, perturbed into an inward trajectory, enters the inner solar system for the first time. This is a moment that can be detected and analysed because dynamically new comets on their first journey from the outer cloud, have distinguishable orbital characteristics from comets that have made previous passes through the inner solar system. A dynamically new comet arrives from the Oort Cloud on a nearly parabolic orbit. Its orbital energy is very close to zero. It is barely bound to the solar system, having been boosted just enough by a galactic tidal perturbation or stellar passage to reduce its perihelion from the outer cloud to the inner solar system. The speed of a dynamically new comet at perihelion is close to the solar system's escape velocity at that distance.
These comets have been in the deep cold of the outer solar system for their entire existence. 60 billion years in near absolute zero conditions. They have never been heated by sunlight at close range. Their surfaces are pristine, the same composition and structure as when they formed. When such a comet enters the inner solar system and begins to be heated by the sun, several things happen that do not happen to comets that have made previous passages. First, the very volatile ices, carbon monoxide, carbon dioxide, that are buried beneath a layer of less volatile material on a previously processed comet, are present at the surface of a dynamically new comet. These hypervolatile species, exposed to the sun for the first time, outgas with extraordinary vigour, driving high activity levels at large distances from the sun, well before the comet reaches the distances where water ice becomes active.
Second, the composition of the outgassing reveals the pristine Oort Cloud chemistry, the specific mix of volatile species that was frozen into the comet at formation, untouched by any prior solar heating. Third, the comet's structure is unprocessed. It has not been consolidated and strengthened by the thermal cycling that repeated passages close to the sun impose on a comet's surface. Dynamically new comets may be more fragile, more susceptible to the structural stresses of solar heating and gravitational tides. Comet C/20020S Ison, a comet that arrived from the Oort Cloud in 20,003 and came very close to the Sun, was expected to be a spectacular comet visible in daylight. It was a dynamically new comet, arriving on its first passage. It was active at large distances, consistent with hypervolatile outgassing from a pristine Oort Cloud surface. But when it reached perihelion, approximately 120,000 million kilometers from the Sun's surface, it disintegrated. The structural fragility of its pristine, unprocessed nucleus could not withstand the extreme tidal forces and thermal stress of the close perihelion passage. Ison's disintegration was both a disappointment for observers and a scientific opportunity. The breakup of a dynamically new comet near perihelion provided direct evidence of the structural properties of Oort Cloud material. Fragile, pristine, structurally different from the consolidated nuclei of short-period comets that have survived many solar passages. Every long-period comet that arrives in the inner solar system is a sample delivery from the Oort Cloud. Every spectrum we take, every composition we measure, every orbital parameter we record is a piece of data about the structure we cannot directly visit. The comets are the Oort Cloud's ambassadors. the only representatives of those 2 trillion distant objects that we can currently study. And each one arrives carrying 4,6 billion years of pristine solar system history, briefly unveiled by the sun's heat before it recedes into the outer darkness or is destroyed in the encounter. This is one of the most profound aspects of solar system science, that the most ancient, most pristine material in our system regularly arrives at our doorstep, briefly offering itself to analysis before departing or disintegrating. We are, through the mechanism of the Oort Cloud and the perturbations that drive comets inward, receiving regular deliveries from the solar system's archives. We have been studying these deliveries for centuries. Every brilliant naked-eye comet in human history was a delivery from the Oort Cloud, providing a brief spectacle before returning to the outer darkness. But only in the last century, with spectroscopic analysis and spacecraft missions to comets, have we developed the tools to read what those deliveries actually contain. And what they contain is extraordinary. The building blocks of planets, the precursors of life's chemistry, the record of conditions billion years ago when the sun was young and the solar system was still forming from its birth cloud. All of it preserved in the near absolute zero darkness of the Oort Cloud, waiting to be delivered to the inner solar system by the slow, inexorable influence of galactic tides and stellar passages. The solar system never ends, because the Oort Cloud is the solar system, the largest, most ancient, most numerous part of it, extending halfway to the nearest star, containing 2 trillion frozen records of our origin. And it is invisible to us, except through the comets that arrive as its ambassadors, briefly luminous, briefly readable, before they depart or are consumed.
Let us now think about something that ties everything together. The specific question of what the Oort Cloud tells us about the nature of boundaries themselves, and why the solar system's refusal to end cleanly is not a failure of definition, but a feature of how gravity actually works. Every boundary we draw in the solar system is a choice, an arbitrary line imposed on a continuous gradient. The heliopause at 120 astronomical units is a real physical transition, the point where solar wind pressure balances interstellar medium pressure. But cross it, and you are not in a categorically different gravitational environment. The sun still dominates. You are still unambiguously in the solar system. The Kuiper Belt's outer edge at approximately pied-dix astronomical units is a statistical feature, a sudden drop-off in the density of trans-Neptunian objects, whose origin is tied to the migration of Neptune in the early solar system. Cross it, and the objects become sparser, but they do not stop. The scattered disk fades gradually into the inner Oort Cloud. Where does one end and the other begin? The distinction is somewhat definitional. Objects with perihelia within Neptune's gravitational influence belong to the scattered disk. Objects with perihelia too distant for Neptune to have placed them there belong to the inner Oort Cloud. Sedna and its relatives occupy the boundary, and the boundary is not sharp. The inner Oort Cloud fades into the outer Oort Cloud. The outer Oort Cloud fades into the Hill sphere boundary. The Hill sphere boundary is itself not sharp. It is defined by the local galactic potential, which varies as the solar system orbits the galaxy. There is no line you can cross that places you definitively outside the solar system in any physical sense. The solar system does not end, it fades. This is how gravity works. Gravity has infinite range. It weakens with distance. The inverse square law is unforgiving in how rapidly it diminishes, but it never reaches exactly zero. There is no distance at which the sun's gravity is precisely zero. There is a distance at which it becomes negligible compared to the galactic background, but negligible is not zero.
The solar system's boundary is wherever you choose to draw a line in a continuous gradient of gravitational influence. Different choices of line give different answers. Different scientific purposes suggest different lines. The heliopause is the appropriate boundary for heliospheric physics. The Hill sphere is the appropriate boundary for orbital stability. The Oort Cloud's outer edge is the appropriate boundary for asking which objects are gravitationally bound to the Sun. None of these is the boundary of the solar system in any absolute sense. All of them are useful approximations to an underlying physical reality that does not have sharp edges.
This is a specific and important lesson about the universe. The universe does not organize itself into neat categories with sharp boundaries. It organizes itself into continuous distributions with gradients. The boundaries we draw between solar system and interstellar space, between one galaxy and another, between matter and vacuum, are human impositions on a physical reality that has no such edges. The Oort cloud illustrates this more clearly than any other structure in the solar system. It is enormous. It is real. It contains trillion objects, and it does not have a clean outer edge. It fades into the interstellar medium, as everything does. Now let us think about the specific experience of what it would be like to be in the Oort cloud, not as an engineering exercise, but as an act of imagination that makes the scale visceral. You are at PDSat T6 astronomical units from the Sun, the middle of the Oort cloud. The Sun, the source of all life on Earth, the object that outweighs every other object in the solar system by 99,86%, the thermonuclear engine that converts 4 million metric tons of its own mass into energy every second, is a star. Bright, far brighter than any other star in the sky, but a star, not a sun, not the overwhelming presence it is from Earth. A bright point of light, magnitude approximately -18,5 by calculation. Very bright, about 1,000,000 times brighter than the full moon is from Earth. But at this distance, it illuminates your surroundings with approximately the same intensity as a candle viewed from 2 meters, spread across the entire sky. It is daylight by no reasonable definition. The sky around you is dark. Stars are visible in every direction, billions of them, the Milky Way arching across the sky as a luminous band, the same constellations visible from Earth, but with the Sun as an additional bright star added to the familiar patterns. You can identify Earth's location, somewhere in the inner solar system, far too distant to see, but in the direction of the Sun. But you cannot see Earth. You cannot see any of the planets. They are invisible at this distance. The entire planetary solar system, all 8 planets and everything within, is a tiny, warm, bright spot centered on the Sun and subtending an angle of less than 1/100th of a degree in the sky. The solar system as you know it, the planetary solar system, everything from the Sun to Neptune, is a dot. A bright dot, much brighter than the stars, but a dot. Around you, in every direction, the Oort cloud. Objects ranging from meters to hundreds of kilometers in size, separated from each other by distances that make the space between Earth and Moon seem crowded. The nearest Oort cloud object to your position might be a few million kilometers away, or it might be hundreds of millions of kilometers away. The cloud is not dense. It just has a lot of objects spread across an enormous volume. The temperature is approximately 4 Kelvin, 4 degrees above absolute zero. Your equipment would need active heating to prevent electronics from failing. Any water would be solid ice of a kind that does not exist naturally on Earth's surface. Ice so cold that the molecular vibrations within it have nearly ceased. The silence is absolute. Not merely the absence of sound, the absence of any medium through which sound could travel. The near-perfect vacuum of the Oort cloud. Fewer particles per cubic meter than the best laboratory vacuum on Earth. You are in our solar system. This
is our solar system. This cold, dark, silent, nearly perfect vacuum, 50 times farther from the Sun than Earth, halfway to the nearest star, too far from the Sun to see its disk, too cold for any volatile chemistry to proceed. This is the largest and most typical environment of the solar system.
The 13 kilometers of atmosphere above Earth's surface. The 6371 kilometers of Earth's radius. The 150 million kilometers to the Sun. The 4,5 billion kilometers to Neptune. All of that is the tiny, warm core of a structure that extends outward for 7.5 trillion kilometers more, to the fading boundary where the Sun's gravity yields to the galaxies. The solar system is this cold, this dark, this empty, this vast. And it never ends. It just gradually fades into something even emptier, even colder, even less attached to any specific star, until you are in the interstellar medium, and then the next star's gravity begins, faintly, to assert itself, and you are in the very outermost, most tenuous reaches of the next solar system. There is no clean line. There is no moment of crossing. There is only the slow fading of one star's gravitational authority and the slow rising of another's. The solar system never ends. It just becomes the universe.
Let us now think about something that gives the Oort cloud a specific emotional weight that goes beyond the scientific. The question of what it means that our solar system contains this vast, invisible structure that we have never directly seen and that no instrument has ever reached. For all of recorded human history, for every civilization that looked at the night sky, catalogued the stars, tracked the planets, measured the seasons, the Oort cloud existed. It existed before we knew it existed, before the concept of a solar system had been articulated, before anyone understood that the Sun was a star, that Earth was a planet, that the other points of light in the sky were other suns separated by incomprehensible distances. When ancient astronomers in Babylon and Egypt and China carefully recorded the positions of the visible planets, the Oort cloud was there, surrounding the solar system in every direction, frozen objects orbiting in the deep cold. When Copernicus proposed that the Earth moved around the Sun, the Oort cloud was there. When Galileo first pointed a telescope at the sky and saw the moons of Jupiter, the Oort cloud was there. When Jan Oort, the Dutch astronomer who first proposed the cloud's existence in working from the orbital statistics of long-period comets, published his theoretical prediction, the Oort cloud was there. As it had been for Chef-Setten billion years, as it will be for billions more. We did not discover the Oort cloud in the sense of first observing it. We inferred it. We reasoned our way to its existence from the properties of the comets that occasionally arrive in the inner solar system. We built a model, mathematically precise, physically motivated, consistent with everything we observe, and the model says the cloud must be there. And we believe the model, because the alternative, that the long-period comets appear without any source reservoir, makes no physical sense.
But we have never seen it. Not a single one of its 2 trillion objects has been directly imaged at its native distance. Not one. The cloud that defines the outer boundary of our solar system, that contains more objects than any other structure in the solar system, that extends to half the distance of the nearest star, is invisible to every instrument we have ever built. This is a strange kind of knowledge, a knowledge that is certain. We are confident the cloud exists, but unconfirmed by direct observation, a knowledge derived from inference and modelling rather than from looking. This is actually a common situation in science, and the Oort cloud is one of the most extreme examples. Dark matter exists, we are confident of this, but we have never directly detected a dark matter particle. The Big Bang occurred. We are confident of this, but no one was present to observe it. Quantum field theory describes the behavior of elementary particles with extraordinary accuracy. But the mathematical objects at its foundation, the quantum fields, have never been directly observed. Science is full of confident knowledge about things that have never been directly seen. The Oort Cloud is one of these things. It is our closest, confident but unseen knowledge. Not billions of light years away, not at the quantum scale, but right here in our own solar system, at distances that are large but not cosmological. The fact that we have never seen it does not make it less real. It makes our confidence in it more remarkable. Confidence built on nothing but the careful analysis of comet orbits, physical models of the solar system's formation, and decades of theoretical refinement. The Oort Cloud is what you get when you apply the laws of physics and the facts of solar system formation rigorously and follow the logic where it leads.
The logic leads to 2 trillion frozen objects extending to 100,000 astronomical units, invisible, ancient, waiting. Now let us think about one more thing, the specific relationship between the Oort Cloud and the concept of home. We speak of the solar system as our home, the place where everything familiar exists. The sun, the planets, the moon, these are the objects that define the context of human existence. We were born in the solar system. We evolved in the solar system. Every human being who has ever lived has spent their entire life within a few light seconds of Earth, well within the inner solar system's compact core. But the solar system as a whole, the structure that bears our name, the gravitationally coherent domain to which the Earth belongs, is almost entirely the Oort Cloud. If you define home as the place you belong to, the place that is gravitationally yours, the structure that claims you gravitationally, then home is not the inner solar system. Home is the Oort Cloud and everything within it. Home is a sphere extending halfway to the nearest star. Home is 2 trillion frozen objects in the deep, cold dark. We have never visited most of our home. We have never even seen it. We live in a tiny, warm corner of an enormous, cold, dark structure, and we mistake that tiny corner for the whole. This is the fundamental redescription the Oort Cloud offers. Not just a correction to the size of the solar system, a correction to the concept of home itself. Your home, the gravitational domain to which you belong, the structure that claims you by the same physics that claims every comet in the outer cloud, extends to 100,000 astronomicznych единиц, to 1,58 light years, to the threshold of the interstellar medium where the sun's gravity finally loses its grip. Every photon of sunlight that falls on those 2 trillion frozen objects, negligible as it is at those distances, barely detectable compared to the cosmic microwave background, is falling on objects that belong to the same gravitational domain as you. They are orbiting the same star. They are bound by the same physics. In the broadest sense, they are your neighbours, very distant neighbours, neighbours in conditions incomparably harsher than where you are, neighbours that have been sitting in their current locations essentially undisturbed for longer than complex life has existed on Earth. But neighbours, part of the same gravitational community. The solar system, your solar system, never ends. It extends to the fading boundary where the sun's gravity yields to the galaxy. It encompasses a volume billion times larger than the planetary disk that your mental picture contains. It holds trillion objects in near absolute zero darkness. It is perturbed by the galactic tide and by the gravity of passing stars. It exchanges material with the interstellar medium, shed from its outer edges by galactic perturbations. And, at its very centre, in the tiny, warm, bright core that your mental picture mistakes for the whole, a small, rocky planet orbits a middle-aged star. And on that planet, organisms have recently developed the capacity to infer the existence of the vast, cold, invisible structure that surrounds them. That inference is one of the most remarkable things that has happened in the Oort Cloud's 4,6 billion-year history. Nothing in the Oort Cloud knows the Oort Cloud exists. We do. Go outside tonight, find a clear sky, let your eyes adjust. Now look up. Pick any direction. North, south, east, west, it does not matter. Look straight up if you prefer. The direction is irrelevant because what we are about to think about surrounds you in every direction simultaneously. In whatever direction you are looking, above you, below you, to every side, the Oort Cloud is there. Not in front of you, in some specific direction you need to find, surrounding you. A sphere of frozen objects extending outward from the sun in every direction, including straight down through the Earth and into the sky on the other side. The Oort Cloud does not have a preferred direction. It encloses the entire solar system like an enormous, tenuous, invisible shell. You are inside it, right now. Standing on the surface of Earth, inside the solar system, you are inside the Oort Cloud. The inner edge of the Oort Cloud, approximately 20,000 astronomical units from the Sun, is above you, below you, to every side, at a distance of 300 billion kilometers in every direction. The outer edge is at 100,000 astronomical units, 15 trillion kilometers in every direction. You are inside the structure we have been describing tonight. Hold that thought carefully, because it changes the geometry of everything else we have discussed. The Oort Cloud is not somewhere else. It is not a distant destination, a place you might someday visit, or that spacecraft might someday reach. It is the outer shell of the structure you already inhabit. It is the walls of your home, if your home is defined by the Sun's gravitational domain. Now hold the numbers we have established. The solar system, the full gravitational domain of the Sun, the full extent of your cosmic home, extends to approximately 100,000 astronomicznych единиц. That is, 1,58 light years in every direction. Light takes 1.58 years to travel from the Sun to the outer boundary of the Oort Cloud. Neptune, the farthest planet, the edge of the planetary solar system that your mental picture contains, is at 30 astronomicznych единиц. The outer edge of the Oort Cloud is at 100,000 astronomicznych единиц. Neptune is 0.3% of the way to the outer boundary of the solar system. The entire planetary solar system, all 8 planets, the asteroid belt, every moon of every planet, everything in the familiar diagram you learned in school, occupies the innermost 0.3% of the solar system's radial extent. The other 99,97% is the Oort Cloud, 2 trillion objects, preserved at 4 Kelvin, 4 degrees above absolute zero, for 4,6 billion years, containing the most pristine chemical record of the solar system's formation. Occasionally perturbed by the gravity of passing stars and the tidal force of the Milky Way, occasionally sending a representative into the inner solar system as a long-period comet, a brief visitor that burns briefly in the sun's heat and then departs, either destroyed or returning to the outer darkness. These comets are the Oort Cloud's only ambassadors, the only representatives of 2 trillion objects that we can observe. And we have been watching them arrive for thousands of years, the brilliant naked-eye comets that appeared in the historical record of every civilization, that terrified medieval populations and inspired astronomical investigation, without knowing what they were announcing. They were announcing the Oort Cloud, delivering samples from the solar system's frozen archive, offering brief glimpses of the structure that surrounds us on all sides that we had not yet learned to read. Jan Oort finally read them in Setu Dievitsot from the orbital statistics of long-period comets he inferred the existence of a vast spherical reservoir at the solar system's outer edge. He inferred its distance, its approximate extent, its basic structure. He did this without ever seeing a single object in the cloud, without any spacecraft having reached it, without any telescope capable of imaging it. From orbital statistics and physical reasoning alone. He was right. That is what the Oort cloud represents scientifically. The success of inference, of careful measurement, of applying physical law rigorously to available data, and following the logic to its conclusion, even when the conclusion is invisible. Now think about what the Oort cloud means for the concept of the solar system's size, and what you have been carrying in your mental picture all along. The familiar diagram, Sun at the center, 8 planets in concentric rings, maybe Pluto indicated as a dotted line beyond Neptune, a suggestion of the Kuiper belt, and then space, the void between us and other stars. That diagram is missing % of the solar system's radial extent. It is missing 2 trillion objects. It is missing the structure that extends halfway to the nearest star. It is not just incomplete. It is a picture of the innermost core of something much larger, presented as if it were the whole. Every mental model you have ever had of the solar system has been a picture of the grain of sand in the middle of the beach, with the beach simply erased. The beach is the Oort cloud, and the beach extends in every direction to 1.58 light years, to the threshold of the interstellar medium, to the boundary where the sun's gravity finally, gradually, yields to the gravity of the galaxy. Now look up again. In the direction you are looking, that specific patch of sky, there are Oort cloud objects, right now. At distances of thousands to tens of thousands of astronomical units, dark and cold and invisible, orbiting the sun on orbital periods of millions of years, undisturbed since before the Earth existed. You cannot see them. No telescope can see them. No spacecraft has reached them. No instrument has detected them at their native distances, but they are there. The same physics that makes an apple fall, that holds the moon in orbit, that keeps Earth circling the sun, that same physics, applied across a distance of thousands of light minutes, holds those 2 trillion objects in their orbits around a star too faint at that distance to be distinguished from the surrounding stars. They are gravitationally connected to you by an unbroken chain of physics. The same sun that rises above your horizon every morning is the gravitational anchor of the Oort cloud. You and those frozen objects, 110 astronomiczych jedinic apart, belong to the same gravitational system. This is your home, the full extent of it. Not the planetary core, not the warm, bright, familiar inner solar system, but everything. The planets, the Kuiper belt, the scattered disk, the inner Oort cloud, the outer Oort cloud, every one of the 2 trillion objects in near absolute zero darkness, all of it, surrounding you in every direction, extending light years, fading into the interstellar medium. You live at the center of this structure, in the warmest, brightest, most chemically active, most biologically hospitable corner of an enormous, cold, dark, mostly empty sphere of frozen time capsules. The solar system never ends. It becomes the Oort cloud. The Oort cloud never ends cleanly. It fades into the interstellar medium. The interstellar medium never ends. It fades into the outer reaches of the next stellar system, and the next, and the next, until you are deep enough into the galactic structure that the concept of belonging to any individual star loses meaning. There are no clean edges. There is no line you can cross that places you definitively outside one thing and inside another. There are only gradients of gravitational dominance, of temperature, of density, of chemical composition. changing continuously from one scale to the next. The solar system is not a bounded object with a clear outside.
It is the region of space within which the Sun's gravity is the dominant force, and that region extends in every direction to 100,000 astronomicznych jedinic. We live at its centre. We did not know this until 1950. We still cannot see it directly. We are confident it is there. Go inside, but remember what surrounds you. Not the familiar diagram with 8 planets and then space. Something larger, something colder, something containing 2 triliona objects older than the Earth, preserved since before complex life existed, waiting in the dark for perturbations that may never come for most of them, occasionally sending one of their number falling inward to briefly catch the sun's light and announce their presence. That is what surrounds you in every direction. 1,58 light years of it. 2 triliona objects. Your solar system. It never ends. Just let it play.